The universe might be a grand illusion. We are about to journey through 50 of the most astonishing theories that tear apart our basic understanding of reality. You will discover ideas that question the nature of time, the fabric of space, and the very meaning of existence. We will explore how a black hole could contain an entire cosmos and why some scientists think our world is a hologram. What hidden truth about reality are you most curious to uncover? Our entire observable universe was once compressed into a single point of infinite density. This is the startling premise of the Big Bang Theory, the cornerstone of modern cosmology. It proposes that everything around us, every star, galaxy, and the very space they inhabit, originated from a singular state of unimaginable heat and density that began expanding some 13.8 billion years ago. We are not talking about an explosion in a pre-existing space, but a rapid expansion of space itself. The universe simply started to grow from that initial point. The evidence for this is etched across the cosmos. Look at the night sky with a radio telescope, and you will hear a faint, static hiss. This is the cosmic microwave background radiation, the cooled remnant of the universe's first light, released when it cooled enough for atoms to form. It is the afterglow of the Big Bang itself, a snapshot of the infant cosmos. Then there is the redshift of distant galaxies. As light travels across the expanding universe, its wavelengths stretch, shifting toward the red end of the spectrum. This tells us that galaxies are racing away from us and from each other, as if we are all on the surface of an inflating balloon. Yet for all its success, the Big Bang Theory leaves us with profound mysteries. What was the trigger, the spark that set this entire cosmic story in motion? The theory describes the expansion but not the initial cause, and perhaps the most baffling question of all: what, if anything, existed before that moment? Was there a before, or did time itself begin with the birth of our universe? But the Big Bang Theory, for all its power, presents its own set of cosmic puzzles. Why does the universe appear so remarkably uniform in all directions? Distant regions of space on opposite sides of the sky have the same temperature, yet according to the standard model, they were never close enough to exchange heat. It is as if two strangers on different continents instantly decided to wear the exact same outfit without ever communicating. This is known as the horizon problem. To solve it, physicists proposed a breathtaking addendum called cosmic inflation. This theory suggests that in the very first sliver of a second, a tiny fraction of a heartbeat after the beginning, the universe underwent a growth spurt of unimaginable speed. It expanded faster than the speed of light, stretching a subatomic speck of space to a size larger than our entire observable universe in less time than it takes to blink. This explosive inflation smoothed everything out, ironing the cosmos into the uniform fabric we see today. It also solved the flatness problem, the mystery of why the geometry of our universe appears so perfectly balanced, neither curling in on itself nor flying endlessly apart. Think of the early universe as a tiny, wrinkled raisin. The force of inflation was like blowing up that raisin into a gigantic, smooth balloon. And just as a balloon might have microscopic imperfections, the quantum foam of the infant cosmos contained tiny fluctuations. Inflation stretched these minute wrinkles into the seeds of all future structure. Those tiny density variations became the gravitational wells that eventually pulled matter together, forming the vast cosmic web of galaxies, clusters, and superclusters we observe today. The entire architecture of our modern universe was imprinted in that first violent moment of expansion. The search for direct proof of inflation continues, with scientists listening for the faintest echo of this event. Primordial gravitational waves, ripples in spacetime itself generated by inflation's ferocious push, would be the ultimate confirmation. Detecting them would be like hearing the distant thunder from the universe's very first storm. If inflation could stretch our universe from a quantum speck, could it also spawn other worlds entirely? This leads us to one of the most staggering ideas in all of science, the multiverse. The theory suggests our cosmos is not unique, but merely one bubble in an infinite cosmic foam of universes, each with its own distinct laws of physics. One prominent model arises directly from cosmic inflation. Imagine a vast, eternally expanding substrate, a background reality where the process of inflation never truly stops. In this roiling sea, pockets of inflation can end randomly, like bubbles forming in a boiling pot of water. Each of these bubbles is a separate universe, cooling and expanding at its own pace, while new bubbles continuously nucleate around it. Our entire observable cosmos is just one such bubble in an endless, ever-growing multiverse. In this picture, the fundamental constants of nature, the strength of gravity, the mass of an electron, might only be local by law. In another bubble universe, these constants could be radically different. Some universes might collapse instantly, while others could be too diffuse for stars to ever form. We simply exist in one where the numbers allow for galaxies, planets, and life. An even more personal version of the multiverse comes from quantum mechanics. The many worlds interpretation proposes that every time a quantum event occurs with multiple possible outcomes, the entire universe splits to accommodate each one. Did a particle go left or right, the universe branches, creating two separate realities, one for each possibility. In this view, every choice you have ever made, every random event that ever happened, spawned a new universe where the alternative played out. There is a version of reality where you took a different job or where the dinosaurs never went extinct. The implications are dizzying. If every possible universe exists, then reality is infinitely richer and stranger than we ever conceived. It challenges our very notion of uniqueness. Are our lives a singular story, or just one thread in an infinite tapestry of what-ifs? Some scientists suggest that if bubble universes can form, they might also occasionally collide. The faint, circular patterns we might one day find etched on the cosmic microwave background could be the cosmic bruises from a long-ago impact with a neighboring universe. The search for such an imprint is a hunt for the ultimate evidence that we are not alone in the grandest sense possible. If every possible universe exists, what are they all ultimately made of? This question drives us to the very edge of theoretical physics, to a theory so elegant and complex it could rewrite the rules of existence. String theory proposes that the most fundamental ingredients of reality are not tiny, solid dots, but unimaginably small, vibrating loops of energy. These strings are so tiny that if an atom were the size of our solar system, a single string would be no larger than a tree on Earth. The music of the cosmos is not in the stars, but in the hum of these infinitesimal filaments. The properties of every particle, every force carrier, are dictated by how these strings vibrate. Think of a guitar string. Pluck it one way and it produces a specific note. Pluck it differently and you get another. In the same way, a string vibrating at one frequency might manifest as an electron. A different resonant pattern could create a quark or even a particle of light. In this framework, the entire universe is a cosmic symphony composed from these fundamental notes. To make this mathematical symphony work, however, the theory demands a shocking expansion of reality itself. We are familiar with the three dimensions of space: length, width, and height, plus the dimension of time. String theory requires more. For the equations to be consistent, there must be at least 6 additional spatial dimensions, curled up into shapes so tiny and complex we cannot perceive them. These are known as Calabi-Yau manifolds. Imagine a garden hose. From a great distance, it looks like a simple one-dimensional line. But if you were an ant crawling on its surface, you would discover a second dimension curled tightly around the hose's circumference. The extra dimensions of string theory are similarly compactified, folded into intricate geometric patterns at every single point in our familiar three-dimensional space. The particular way these dimensions are folded determines the vibrational modes of the strings. which in turn dictates the laws of physics in our universe. A different fold would produce different constants and forces. This offers a potential explanation for why our universe has its specific set of rules, and it even connects back to the multiverse idea, where each bubble universe could have its own unique Calabi-Yau geometry. The ultimate promise of string theory is a theory of everything, a single framework that seamlessly unites the colossal world of gravity, governed by Einstein's general relativity, with the bizarre quantum realm of the very small. For decades, these two pillars of physics have been fundamentally incompatible. Yet string theory naturally incorporates gravity, with the graviton, the hypothetical particle that carries the gravitational force, emerging as just another vibrational mode of a string. The challenge and the great criticism of the theory is its current lack of testable predictions. The strings and the extra dimensions exist at energy scales far beyond the reach of any particle accelerator we could ever build. For now, it remains a breathtakingly beautiful mathematical landscape, a vision of a unified cosmos whose ultimate truth is still just beyond our grasp. String theory's extra dimensions are a profound idea, yet an even more radical concept suggests that all those dimensions, including our own, might be nothing but a magnificent illusion. The holographic principle proposes that our seemingly solid, three-dimensional universe is actually a hologram, a projection of information encoded on a distant, two-dimensional surface. Just as a credit card security hologram emerges from patterns etched on flat film, our reality of depth, volume, and space could be a translation of data stored at the cosmic edge. This bizarre idea finds its roots in the most enigmatic objects in the cosmos, black holes. When matter falls into a black hole, it seems to vanish, but the laws of quantum mechanics insist that information can never be truly destroyed. So where does it go? Physicists discovered that the maximum amount of information a region of space can contain is not proportional to its volume, as you might expect, but to the area of its boundary. A black hole's internal information appears to be entirely encoded on its two-dimensional event horizon, the point of no return. It is as if the contents of a book were not written on pages throughout its volume, but were perfectly stamped onto its outer cover. If this is true for black holes, the ultimate prisons of information, could it be true for our entire universe? Our cosmic horizon, the furthest limit of what we can observe, might act as that two-dimensional surface, a vast cosmic hard drive storing the bits that project our three-dimensional existence. Every star, every person, every feeling you have would be a holographic translation of data living on that distant boundary. This shatters our intuitive understanding of reality. The solidity of your hand, the vast emptiness of space between galaxies, the very passage of time, all could be emergent properties of a deeper, simpler, two-dimensional reality. We are not just in the universe, we are a projection of it. The world we experience would be a kind of cosmic cinema, a convincing illusion rendered in real time from a fundamental layer we cannot directly perceive. Are we living in a simulation, not necessarily one built by machines, but one generated by the very laws of physics, a reality where the deepest truths are written not in three dimensions but in two? The holographic universe is a profound abstraction, but there is a tangible, invisible presence that sculpts the cosmos on the grandest scales. We can observe its gravitational handiwork everywhere, from the whirling dance of galaxies to the very architecture of the cosmos, yet its true identity remains one of science's greatest enigmas. This is the mystery of dark matter. It is not a shadowy version of ordinary matter. It does not emit, absorb, or reflect any light, making it completely transparent and undetectable to our telescopes. We only know it is there because of the powerful grip it exerts on the things we can see. The first compelling clue came from the rotation of galaxies. According to the laws of gravity, stars on the outer edges of a spiral galaxy should orbit much more slowly than those near the bright, dense center, just as Pluto moves more sluggishly around the Sun than Earth does. Yet when astronomers measured these galactic rotation curves, they found something astonishing. The outer stars were racing around just as fast as the inner ones. It was as if the entire galaxy was spinning like a solid plate. The only explanation is that each galaxy is embedded within a vast, massive halo of something invisible, a spherical cloud of dark matter whose gravity is pulling on those distant stars, preventing them from flying off into intergalactic space. Another line of evidence comes from gravitational lensing. Einstein's theory tells us that massive objects warp the fabric of space-time, bending the path of light that travels near them. Sometimes we see distant galaxies whose light has been distorted and magnified by an unseen foreground mass, creating multiple images, arcs, and rings in the sky. The amount of bending is often far too severe to be caused by the visible matter alone, revealing the presence of immense, invisible concentrations of dark matter acting as a cosmic lens. So what could this mysterious substance be? The leading candidates are not stars or planets, but exotic particles born in the early universe. One prominent hypothesis points to WIMP, or weakly interacting massive particles. These are theoretical heavy particles that do not interact with electromagnetic force, meaning they pass straight through normal matter like ghosts through a wall. Vast experiments deep underground are searching for the rare, telltale jiggle an atom would make if a WIMP ever bumped into it. Another compelling candidate is the action, an extremely light particle trillions of times less massive than an electron. While individually insignificant, actions could flood the universe in such unimaginable numbers that their collective gravity would account for the missing mass. Think of dark matter as the invisible scaffolding of the cosmos. When the universe was young, its ordinary matter was too hot and energetic to clump together effectively. But dark matter, unaffected by light and radiation, could already begin to coalesce under its own gravity. It formed a vast, webbed framework, and the normal matter, the stuff of stars and planets, simply flowed into the gravitational wells it created. Every galaxy we see today is just a glittering ornament hanging on an unseen dark matter skeleton. Without this hidden architecture, galaxies would never have formed, and the universe would be a dark, featureless sea of drifting gas. We are surrounded by this ghostly substance, living our lives while trillions of these unknown particles stream through our bodies every second, completely unnoticed. Its discovery forces us to accept a humbling truth that the universe is dominated by something we cannot see, a silent partner in the cosmic dance that holds the very fabric of reality together. Dark matter provides the cosmic glue that holds galaxies together, but an even more dominant and enigmatic force is working in the opposite direction, relentlessly tearing the universe apart. This is the mystery of dark energy. While dark matter pulls with its gravity, dark energy appears to be a repulsive force, a kind of anti-gravity woven into the very fabric of empty space. It constitutes a staggering 68% of the total energy content of the cosmos, making it the single most powerful influence on the universe's ultimate destiny. Its discovery in the late 1990s was a monumental shock that overturned decades of scientific consensus. Astronomers were observing distant stellar explosions known as Type I, a supernova. These events are cosmic standard candles, meaning they always explode with the same intrinsic brightness. By measuring how dim they appear from Earth, scientists can calculate their distance with remarkable precision. They expected to find that the expansion of the universe, set in motion by the Big Bang, was gradually slowing down due to the collective gravitational pull of all the matter in the cosmos. Instead, they found the opposite. The most distant supernovae were significantly fainter than they should have been, meaning they were much farther away than anyone had predicted. The expansion of the universe was not slowing down, it was accelerating. Galaxies are flying away from each other at a pace that grows faster with every passing moment. It was as if you tossed a ball into the air, only to watch it not just continue upward but hurtle away from the Earth at an ever-increasing speed. So what is this bizarre force? The leading candidate is the cosmological constant, an idea that Albert Einstein himself proposed and later called his greatest blunder. He originally inserted it into his equations to achieve a static universe, but then discarded it when Edwin Hubble discovered the universe was actually expanding. Now, it seems he may have been right for the wrong reason. The cosmological constant suggests that dark energy is an inherent property of the vacuum of space itself. Empty space is not truly empty according to quantum physics. It seethes with virtual particles that flicker in and out of existence. This quantum activity gives the vacuum a constant, low-level energy density. As the universe expands and more space comes into being, this vacuum energy increases, driving the expansion ever faster. Another possibility is that dark energy is not constant at all, but a dynamic force field that has changed over time. This concept is known as quintessence, named after the fifth element of ancient philosophy. Unlike the steady push of the cosmological constant, quintessence could vary in strength, perhaps even changing from an attractive force in the ancient past to the repulsive force we observe today. The nature of dark energy dictates the ultimate fate of our cosmos. If it is a true cosmological constant, the acceleration will continue indefinitely. Galaxies will be pulled so far apart that their light can no longer reach us. The sky beyond our local group of galaxies will become utterly black and empty. Stars will burn out, and the universe will approach a state of maximum entropy, a dark, cold, and lifeless end known as the Big Freeze or heat death. But if dark energy is something more potent and strange, like a form of quintessence that grows stronger over time, the outcome could be far more violent. In a scenario called the Big Rip, the accelerating expansion would eventually overcome all other forces. First, galaxy clusters would be torn apart, then individual galaxies. As the end draws near, the repulsive force would rip stars from their galaxies and planets from their stars. In the final moments, even atoms and atomic nuclei would be shredded, tearing the very fabric of reality apart at the smallest scales. The universe would end not with a whimper, but with a catastrophic, instantaneous disintegration of spacetime itself. The relentless expansion driven by dark energy paints a bleak picture of an ultimate end. But what if this is not the universe's first or last chapter? A compelling alternative suggests our cosmos is engaged in an eternal, rhythmic dance of death and rebirth. This is the theory of the Big Bounce, a cyclic model where the universe undergoes endless cycles of expansion and contraction. Instead of a single, unique beginning from nothing, our Big Bang was merely the most recent turn in an infinite cycle. In this view, the universe expands from a hot, dense state, just as we observe, but eventually, the collective gravitational pull of all matter and energy halts the expansion. The cosmos then reverses course, collapsing back in on itself in a cataclysmic event known as the Big Crunch. It does not simply vanish, however. The theory proposes that at the moment of maximum compression, when all reality is crushed into an unimaginably hot, dense state, the laws of physics as we know them transform. A quantum repulsion, a kind of cosmic bounce, occurs, triggering a new period of expansion and another Big Bang. This process repeats forever with no beginning and no end. This elegantly sidesteps the perplexing initial singularity problem of the standard Big Bang model, the baffling question of what came before and why it happened. In the cyclic universe, there is no before the beginning because there was no absolute beginning, only an endless, breathing rhythm of cosmic renewal. The search for evidence of a previous cycle is a primary focus for cosmologists. If our universe was born from the ashes of a prior one, there might be faint imprints left behind. One promising place to look is the cosmic microwave background, the ancient light from the infant universe. Scientists are meticulously analyzing this radiation for any signs of concentric circular patterns, which could be the gravitational wave echoes of a colossal collision between our universe and another in the previous cycle, or the scars left by the bounce itself. Finding such a pattern would be like discovering a fossil from a cosmos that existed before our own. Imagine the entire history of our universe, all 13.8 billion years of star formation, galaxy evolution, and the rise of life, as just one single exhalation in an eternal cosmic breath. Each cycle could last trillions of years, with galaxies forming, stars burning out, and perhaps even life arising, only to be gathered back into the fiery forge of the crunch, all its information and structure scrambled, yet providing the raw material for the next universe. In this grand vision, an end is never truly an end, but merely a transformation, a reset for another iteration of reality. This rhythmic cycle of cosmic death and rebirth finds a startling new form in the ekpyrotic universe. Picture our entire three-dimensional reality not as an isolated cosmos, but as a vast, flexible membrane or brain floating within a higher dimensional realm. This grander space is known as the bulk. Our brain is not alone, it exists parallel to another, separated by a tiny gap in this hidden dimension. The Big Bang in this radical picture was not an explosion from a point, but the shattering aftermath of a collision between our brain and its neighboring one. Imagine two enormous sheets of rubber drifting silently in an unseen space until they gently smack into each other. The energy of that impact was so immense that it flooded our brain with radiation and matter, heating it to incredible temperatures and setting off the expansion we observe today. This idea springs directly from string theory, which provides the necessary higher dimensional playground for such brains to exist. Unlike the Big Bounce, which involves the entire universe collapsing and rebounding, the ekpyrotic model is a collision in a hidden dimension, a reset triggered from the outside. After the collision, the two brains bounce apart, stretched and energized. They then slowly drift back toward each other over eons, drawn by a force across the bulk, setting the stage for the next cosmic collision and the next cycle of creation. The echoes of such a primordial event might still be rippling through the cosmos today. As these colossal membranes collided, they would have sent powerful tremors through space-time itself, generating a unique background of gravitational waves. Our most sensitive observatories are now listening for this faint cosmic hum, a specific pattern woven into the fabric of reality that would be the definitive signature of a universe born from a collision. Finding it would not just confirm a new theory of the Big Bang, it would prove we are part of a much larger, multidimensional reality, where our entire history is just one chapter in an endless, echoing dance of celestial sheets. This branching of worlds holds a startling implication for the very experience of being alive. Quantum immortality is the philosophical proposition that your conscious awareness can never truly witness its own end. The logic flows directly from the many worlds interpretation of quantum mechanics. Every time a situation arises that could lead to your death, the universe splits. In one branch, the fatal outcome occurs, but in at least one other branch, you survive by some improbable quantum fluctuation. Your stream of consciousness, the subjective feeling of being you, can only follow the path where you continue to exist. You are, from your own perspective, unkillable. To illustrate this, physicists devised a gruesome thought experiment known as quantum suicide. Imagine a device is set up that points a gun at your head. The trigger is linked to a quantum event like the decay of a radioactive atom. In any given second, there is a 50% chance the gun will fire. You pull the trigger once. In one branch of the multiverse, the atom decays, the gun fires, and that version of you ceases to be. But in another branch, the atom does not decay, the gun does not fire, and you remain alive. You pull the trigger again, the universe splits. From your subjective point of view, you will only ever experience the sequence of universes where the gun repeatedly fails to fire. No matter how many times you pull the trigger, you will always find yourself alive, miraculously surviving against all odds. To an outside observer, you would appear to be extraordinarily lucky for a while, until statistically, you are almost certainly dead in the vast majority of realities. But you, the subject of the experiment, would never experience that death. You would simply continue on, perhaps baffled by your own incredible luck. This forces us to confront deep questions about consciousness. Is consciousness a single thread, or does it branch with the universe? The theory suggests your awareness is not a copy that spreads across all worlds, but a single path that persistently follows the timeline where it is sustained. It proposes a terrifying form of immortality where you might survive a global catastrophe or even the heat death of the universe through an endless series of statistically impossible quantum escapes. Your life would become a never-ending story, navigating through an ever-thinning set of realities where conditions against all odds still permit your conscious existence. This is not a pleasant immortality, but a logical consequence of a branching multiverse where every possibility is realized. It reduces death from a finality to a perspective, an event that happens to other versions of you, but never to the you that is reading these words right now. The world you perceive is simply the one consistent with your continued observation. Quantum immortality suggests a universe that constantly branches to preserve consciousness, but what if that entire branching structure is not the ultimate reality, but something far more artificial? The simulation hypothesis proposes that our universe is not base reality, but an advanced digital construct, a simulation running on the computer of a vastly more developed civilization. Our entire existence, from the furthest galaxy to the feeling of sunlight on your skin, could be nothing more than lines of code in a post-human project. This is not science fiction, but a serious argument considered by philosophers and technologists. One of the most compelling reasons to take this idea seriously is the deeply mathematical nature of our universe. The laws of physics are not just described by mathematics, they seem to be written in it. From the elegant equations of general relativity to the probabilistic rules of quantum mechanics, reality appears to run on a set of discrete, computable rules, much like the code underlying a complex video game. Furthermore, there appears to be a fundamental resolution to our reality, a smallest possible unit of space and time. This is the Planck length and Planck time, scales so tiny they are beyond human comprehension. At this level, the smooth continuity of space and time might break down into a kind of pixelation, just as a digital image reveals its blocky pixels when you zoom in too far. This pixelated foundation of reality is exactly what you would expect if the universe were running on a computer with finite processing power. The creators of this simulation, often hypothesized to be our own descendants, would possess technology so advanced that their computing power is indistinguishable from magic. They might be running countless such simulations, perhaps as a form of historical research, a scientific experiment, or even for entertainment. If that is the case, then the vast majority of conscious beings would not be in the original, base reality, but inside one of these simulated worlds. Statistically, it is far more likely that we are among the simulated minds. This leads to profound philosophical questions. If we are in a simulation, what are the ethical rules governing our creators? Are they benevolent scientists observing us, or careless gamers who might shut down the server on a whim? The glitches and anomalies we sometimes perceive in reality, moments of déjà vu or unexplained phenomena, could be seen as bugs in the code or patches being applied by the system administrators. The very fabric of our perceived reality becomes uncertain. The solid ground beneath your feet, the air you breathe, the love you feel for others, all of it would be a perfectly rendered illusion, a sensory input fed directly to your simulated consciousness. Your entire life, with all its triumphs and tragedies, could be a single, intricate narrative thread in a simulation designed for a purpose you cannot fathom. This does not make your experiences any less real to you, but it fundamentally alters their meaning. We are left to wonder if the mysteries we are unraveling, the very laws of physics we are discovering, are merely the user manual for a reality we did not build. This unsettling idea forces us to question the very reliability of our memories. The Boltzmann brain is a thought experiment born from the deep laws of thermodynamics, suggesting that in a vast and eternal cosmos, the most likely form of consciousness is not one that evolved over billions of years, but one that just randomly assembled, complete with false memories of a past that never was. It comes from the concept of entropy, the universal tendency toward disorder. In any closed system, things will almost always move from a state of order to a state of chaos. A shattered glass does not reassemble itself, and a hot cup of coffee will always cool to room temperature. Yet the statistical laws that govern this process do not forbid order from arising by pure chance, they just make it extraordinarily improbable. In a truly infinite or eternally inflating universe, given enough time, every possible configuration of matter, no matter how unlikely, will eventually occur through random quantum fluctuations. The spontaneous formation of a fully formed, self-aware brain, complete with a lifetime of fabricated memories, is statistically far more probable than the gradual evolution of an entire, ordered cosmos spanning billions of light years. Think of it like this: shaking a box of Scrabble letters will almost certainly produce a random jumble, but if you shake that box for an eternity, there will eventually be one moment where the letters fall and spell out a perfect Shakespearean sonnet. The Boltzmann brain argument says that you are far more likely to be that single, fleeting, sonnet-spelling arrangement than a real person who actually learned the sonnet through years of study in a stable universe. Your entire life, everything you believe you have experienced, could be an illusion. The room you are in, the device you are listening on, the very cosmos you think you inhabit might not be real. They could be nothing more than the detailed, immersive hallucinations of a lone brain that just popped into existence a moment ago, floating in the void, believing itself to have a history. This is not a proposal that scientists believe is true, but rather a profound philosophical puzzle that highlights a crisis in our understanding of cosmology. If our best models of an eternal universe inevitably lead to the conclusion that we are more likely to be random fluctuations than real beings, then perhaps those models are fundamentally flawed. The Boltzmann brain is a ghost at the feast of cosmology, a constant reminder that our grasp on reality is far more fragile than we dare to admit. It suggests that the greatest cosmic mystery may not be out in the distant galaxies, but locked within the confines of your own mind, questioning whether any of your memories are truly your own. If a black hole is a cosmic drain from which nothing escapes, then its theoretical opposite is a brilliant, unapproachable fountain. This is the concept of a white hole, a region of space-time that can only expel energy and matter, forbidding anything from ever crossing its boundary inward. It emerges not from wild speculation, but as a valid, if bizarre, mathematical solution to Einstein's field equations of general relativity. In the stark language of physics, a white hole is simply a black hole running backward in time. Where a black hole's event horizon is a point of no return, a white hole's horizon is a point of no admission. You could no more enter one than you could catch a cannonball fired directly at you and throw it back into the cannon's barrel. Imagine a celestial geyser of pure energy, shining with impossible brilliance, yet completely unreachable, its outpouring of light and matter forever barred to any visitor. One of the most tantalizing ideas is that a white hole could be the other end of a black hole, perhaps connected by a space-time tunnel known as a wormhole. Matter that vanishes into a black hole could, in this theory, be violently reborn, spewed out into another universe or a different part of our own. This offers a potential escape from the terrifying fate of black hole destruction, a cosmic rebirth on the other side of the veil. Some cosmologists have even proposed that the Big Bang itself was a primordial white hole event. the ultimate expression of a singularity erupting and creating our entire cosmos from a single point of infinite energy. Could the birth of our universe have been the final, spectacular output of a white hole in a parent cosmos? More recently, white holes have been suggested as a potential explanation for certain mysterious, intensely powerful cosmic explosions. When astronomers detect a colossal burst of energy from the depths of space, one that does not fit the profile of a supernova or a gamma-ray burst, could they be witnessing the brief, glorious eruption of a white hole? A one-time event where a black hole connection finally severed, causing its white hole counterpart to violently expel all of its accumulated mass and energy in a single universe-shaking flash. While no definitive evidence for a white hole has ever been found, their existence forces us to consider the profound symmetry of the cosmos, a universe where every entrance might have an exit, and every end could be a new beginning in disguise. White holes present one end of a cosmic tunnel, but the full passage is even more astonishing. Wormholes, often called Einstein-Rosen bridges, are theoretical shortcuts woven into the fabric of spacetime itself. Predicted by Einstein's theory of general relativity, these are not tunnels dug through space, but bridges that connect two distant points by folding the cosmos. Imagine spacetime as a vast sheet of paper. To get from a dot on one side to a dot on the other, you would normally travel the long way across the entire page. But if you fold the paper so the two dots touch, you have created a bridge, a wormhole, making the journey instantaneous. These cosmic shortcuts could link stars thousands of light years apart, or even connect entirely separate universes in the multiverse. The mathematics is sound, but the physical reality is fraught with peril. A natural wormhole would be incredibly unstable, snapping shut in a fraction of a second, crushing anything attempting to pass through. To keep one open for travel, you would need a bizarre and hypothetical substance known as exotic matter. This is not just unusual material, but matter that possesses negative energy density, effectively having negative gravity. While this sounds like pure fantasy, quantum physics allows for the existence of such states on a microscopic scale, in what is known as the Casimir effect. To prop open a traversable wormhole, however, you would need a vast quantity of this exotic matter, something far beyond our current understanding or capabilities. This negative energy would act as a kind of anti-gravitational force, pushing the throat of the wormhole open against its own immense gravitational pull, preventing the tunnel from collapsing into a singularity. The implications of a stable wormhole are staggering. It would be the ultimate tool for faster-than-light travel, not by moving through space faster than light, but by taking a shortcut that makes the journey shorter. A spaceship could enter a wormhole near Earth and emerge moments later in a galaxy millions of light years away, effectively traveling across the universe without breaking the universal speed limit. This also opens the door to the possibility of time travel. According to general relativity, if one end of the wormhole is moved at a significant fraction of light speed or placed near an intense gravitational field like a black hole, time would flow slower for that end compared to the stationary end. If you were to then travel through the wormhole, you might exit not just in another place, but in another time, stepping into the past or the future. The challenges, however, are as immense as the possibilities. Creating or finding a stable wormhole is one thing, but navigating it is another. The interior could be buffeted by violent gravitational tides and filled with intense radiation. Furthermore, the mere act of sending even a single particle through could trigger a catastrophic feedback loop of radiation, destroying the tunnel entirely. A journey through a wormhole would be the ultimate cosmic voyage, a surreal passage through a glowing, kaleidoscopic tunnel where the laws of physics as we know them are stretched to their absolute limit. While wormholes bend the rules of space, a new discovery challenges the very definition of time. Time crystals are a bizarre phase of matter that was once thought impossible, a structure that moves in its ground state, its most stable and lowest energy form. Imagine a clock that ticks forever without ever needing to be wound. Every other object in the universe, when cooled to absolute zero and left alone, settles into a motionless, inert state. A time crystal does the opposite. It begins to oscillate, repeating a pattern not in space but in time. It ticks with a regular, unwavering rhythm, all without consuming any energy. This perpetual motion is not a violation of physics, but a subtle dance with its laws, a phenomenon that breaks what scientists call time translation symmetry. This simply means that the crystal state is not the same at every moment in time, unlike a stationary rock or a still glass of water. Its structure evolves in a predictable, periodic loop, forever marking the passage of time from within its own frozen architecture. Scientists create these crystals in labs using complex systems, like chains of ions or dense clouds of atoms, manipulating them with precise laser pulses to kick-start this eternal ticking. The resulting oscillation is not a physical vibration you could feel, but a coordinated flip in the quantum properties of the entire system, a heartbeat that continues indefinitely without friction or energy loss. This has profound implications for the technology of the future. In quantum computing, where fragile quantum states are easily disrupted, time crystals could act as perfect, self-sustaining clocks. They could synchronize operations within a quantum processor, protecting the delicate calculations from decoherence and errors, potentially unlocking unprecedented computational power. But beyond their practical use, time crystals force us to reconsider a fundamental question. What is time? We often think of it as a relentless, uniform flow, an arrow moving in one direction. Yet here is a physical object that embodies a pure, perfect rhythm, a clock whose ticking is an intrinsic property of its quantum structure. It suggests that time itself may have a granular, discrete nature at the most fundamental level, and that such perpetual cycles could be a hidden property of reality, ticking away in the quantum background of the cosmos. We are discovering that matter can be ordered not just in space, but in time itself, revealing a new dimension of existence where motion and stability become one and the same. This branching of reality is not just a philosophical quirk, but a concrete proposal with a name: the many worlds interpretation. Physicist Hugh Everett offered this radical vision not as science fiction, but as a serious alternative to the dominant view of quantum mechanics. For decades, the Copenhagen interpretation has held sway, suggesting that a particle exists in a blurry cloud of potential, a superposition of all possible states until the moment it is observed. This act of measurement, like a cosmic judge, forces the particle to choose a single, definite reality, collapsing the wave function into one outcome. A radioactive atom is both decayed and not decayed until you look at it, at which point it picks a state. Everett found this deeply unsatisfying. Why should consciousness have such a privileged role in shaping reality? His solution was breathtakingly simple and profound. He proposed that the wave function never collapses. Instead, every time a quantum event occurs with multiple possible outcomes, the entire universe physically splits to accommodate each and every one. That radioactive atom does not choose. In one newly formed branch it decays. In another, it remains stable. The universe has branched, and both outcomes are now equally real, playing out in parallel worlds that are forever disconnected. This eliminates the need for a mysterious observer, making the entire process objective and mechanical. The consequences of this are almost impossible to fully grasp. Every single quantum event, and there are trillions occurring every moment, spawns new universes. Every time an electron jumps to a new energy level, every random mutation in a strand of DNA, every unpredictable decay of an atom, the cosmos fractures. This means there is a reality where you are reading this script in a different color, and another where a cosmic ray prevented your ancestors from ever meeting. The tree of reality is infinitely branching, with every possible history and future actually existing somewhere in the vast multiverse. This idea forces us to confront the nature of our own choices. That job you did not take, the person you never spoke to, the lucky break you got in another world, the alternative happened. There is a version of you living with the consequences of every road not taken. This is not a metaphor, but a proposed physical reality. The you in this universe is just one thread in an infinite tapestry of selves, so why do we not feel this splitting? Why are we unaware of these other versions of ourselves? The theory suggests that after a branch occurs, the different worlds decohere. They phase out of sync with each other, becoming mutually invisible and uncontactable, like radio stations broadcasting on different frequencies. Your conscious awareness is locked into the single branch that you call your life, forever flowing forward along one timeline in the ever-expanding labyrinth of realities. This leads to the unsettling question of identity. Are you a unique individual, or merely one instance of a vast collection of beings who all share your history up until the last quantum decision? The many worlds interpretation does not just populate the cosmos with stars and galaxies, but with every possible story that could ever be told, each one real, each one unfolding in its own separate, shimmering branch of existence. Our relentless forward march through time may be the most persistent illusion of all. General relativity paints a picture of reality that is utterly static, a cosmos where the past, present, and future are equally real and exist forever. This is the theory of the block universe, a four-dimensional structure where time is simply another dimension, much like length, width, and height. In this frozen tapestry, every event that has ever happened or ever will happen is fixed in its place, a permanent part of the cosmic landscape. Your birth, your first day of school, and your last breath are all out there, not as memories or possibilities, but as concrete coordinates in the vast block of space-time. This challenges our most fundamental experience, the feeling of a flowing now that sweeps us from a fixed past into an open future. According to the block view, this flow is a trick of consciousness. We are like a passenger on a train, moving along the tracks of our own world line, illuminating one moment at a time with the spotlight of our awareness. But the entire railway, from the station of your birth to the final terminus, is already built and complete. This has profound implications for the concept of time travel. If the past is not gone but simply located at a different address in the four-dimensional continuum, then traveling to the past would not be about changing history, but about navigating to a different part of the block. You would be visiting a region that has always contained your arrival, just as traveling to Paris is about moving through space to a place that already exists. Your journey to the past would have been part of that past all along, a fixed thread woven into the timeless fabric. This view, known as eternalism, stands in stark opposition to presentism, the intuitive belief that only the present moment is real. For a presentist, the past is gone and the future is not yet written. A constantly renewing now is the sole reality. The debate between these two ideas is one of the oldest in philosophy, but physics has thrown its weight behind the block universe. The relativity of simultaneity proves that there is no universal now. Two events that are simultaneous for one observer can happen at different times for another moving at high speed. If there is no single, privileged present moment that everyone in the universe can agree on, how can it be the only thing that is real? The block universe offers a democratic solution where every moment from every perspective holds equal reality. This can feel deeply unsettling, as it seems to rob us of free will and the novelty of a truly open future. Yet it also offers a strange kind of comfort, a vision of a cosmos where every cherished memory and every hopeful dream is eternally preserved, not as a ghost, but as a permanent feature of reality itself. While string theory adds hidden dimensions, another powerful idea rewrites the rules of our familiar four. Quantum loop gravity proposes that space itself is not a smooth, continuous stage but a fabric woven from a billion tiny, indivisible loops. These loops are the fundamental pixels of reality, a network of vibrating threads so small that 1 trillion of them could fit across a single atomic nucleus. Where string theory posits vibrating strings within space, loop gravity suggests that space itself is made of strings woven together into a dynamic web. This cosmic tapestry is known as a spin network, and its evolution through time creates a complex structure called a spin foam, a frothing sea of these interconnected loops that defines the very geometry of the cosmos. This solves one of physics' greatest embarrassments, the dreaded singularity. In Einstein's general relativity, the centers of black holes and the moment of the Big Bang are points of infinite density where the laws of physics break down. But in loop gravity, you cannot compress space beyond its fundamental grain. The loops push back, creating an immense repulsive force that prevents the universe from ever reaching a true singularity. The Big Bang was not an explosion from nothing, but a great bounce from a previous cosmic phase, a rebound driven by the quantum structure of space itself. What existed before our universe, perhaps a collapsing cosmos that reached its minimum size and then bounced outward, giving birth to the expanding reality we inhabit today. This theory paints a breathtaking new picture of our world. If you could peer down to the Planck scale, space would not appear smooth and empty. It would look like a frenetic, ever-changing foam, a quantum storm where tiny loops of space-time constantly reconnect and reshape the geometry of reality. Your hand, the air, the distant stars, all are vast, smooth patterns emerging from this unimaginably fine-grained, shimmering network. The solid ground beneath your feet is an illusion of scale, a calm surface over an ocean of quantum turbulence. The search for the fundamental grains of reality has revealed a troubling imbalance. Our two greatest theories, the standard model of particle physics and general relativity, are built on foundations that do not quite match. One describes a quantum world of frantic particles, the other a smooth, geometric spacetime. But what if this disconnect is not the final word? Supersymmetry is a beautiful and powerful idea that proposes a deep, hidden symmetry woven into the very fabric of the cosmos, a symmetry that could bridge this chasm. It suggests that for every known particle in the universe, there exists a massive, undiscovered superpartner. For every matter particle like an electron, there should be a force-carrying partner called a selectron. For every force carrier like the photon, there should be a matter partner known as the photino. This doubles the number of fundamental particles, creating a shadow world of superparticles waiting to be discovered. One of the most compelling reasons physicists are so drawn to this idea is its potential to solve the hierarchy problem. This is the puzzle of why the force of gravity is so unimaginably weaker than the other fundamental forces. The electromagnetic force is a trillion times stronger than gravity. This is a number so large it seems absurd, like comparing the weight of a single bacterium to the mass of our entire galaxy. In the standard model, this vast difference is an arbitrary, fine-tuned number with no explanation. But supersymmetry offers a natural solution. It proposes that the contributions of ordinary particles to the mass of the Higgs boson are perfectly cancelled out by the contributions of their superpartners. It is a cosmic balancing act where the push of one type of particle is exactly countered by the pull of its shadow. This would explain why the Higgs boson is light enough to allow atoms to form, and ultimately why our universe can support complex structures like us. Beyond this, supersymmetry provides a perfect, and perhaps the most compelling, candidate for the mysterious substance holding galaxies together, dark matter. The lightest of these superpartners, often thought to be the neutralino, would be stable, electrically neutral, and only interact through gravity and the weak nuclear force. This fits the profile of dark matter perfectly. Trillions of these particles could be streaming through you at this very moment, completely unnoticed, their collective gravity providing the invisible scaffolding for the entire cosmic web. Finding these particles would not just complete our particle zoo, it would solve one of the greatest mysteries in modern cosmology. For decades, the hunt for these superpartners has been a primary mission for the world's most powerful particle accelerator, the Large Hadron Collider. Scientists hoped that by smashing protons together at velocities approaching the speed of light, they could create enough energy to conjure these massive superpartners into existence, even if only for a fleeting moment. The experiments have been meticulous, the data analysis exhaustive, yet so far the detectors have found nothing: no selectrons, no photinos, no squarks. The shadow world remains stubbornly hidden. This profound absence is forcing a major rethink. Perhaps supersymmetry is not exactly as we imagined. Maybe the superpartners are far heavier than we hoped, placing them beyond the reach of our current machines. Or perhaps the beautiful symmetry is subtly broken in ways we have not yet conceived. The silence from the collider is not a death knell for the theory, but it is a clear message that the universe is even more mysterious and elusive than our most elegant equations predicted. The eerie silence from our particle colliders forces a humbling question. Why does our universe seem so perfectly tailored for our existence? The fundamental constants of nature, the precise strength of gravity, the exact mass of an electron, appear to be balanced on a razor's edge. If gravity were just slightly stronger, the universe would have collapsed back on itself in a fiery crunch moments after the Big Bang. If the force binding atomic nuclei were a fraction weaker, hydrogen would be the only element, and no complex atoms, no stars, no planets could ever form. This cosmic fine-tuning is the puzzle addressed by the Anthropic Principle, a philosophical idea with profound scientific implications. The weak Anthropic Principle offers a straightforward, almost tautological answer. We observe a universe with these specific constants for one simple reason: we are here to observe it. In a cosmos where the numbers were even slightly different, life would never have arisen, and there would be no one to wonder about the laws of physics. It is like a lottery winner marveling at their incredible luck without considering the millions of other tickets that lost. The weak principle simply states that our observations are biased by the requirement for our existence as observers. The strong Anthropic Principle takes a much more controversial leap. It suggests that the universe must have properties that allow life to develop at some stage in its history. This version edges into teleology, the idea that the cosmos has a purpose or a goal, which is the emergence of conscious life. For some, this implies a kind of cosmic design, though it does not specify a designer. For others, it is a statement about the necessary conditions for a universe to be observable in the first place. The most compelling scientific resolution to this fine-tuning puzzle comes from the multiverse. If an infinite number of universes exist, each with its own random set of physical constants, then it is no surprise that we find ourselves in one of the rare habitable ones. In this vast cosmic landscape, most universes are stillborn or barren, incapable of supporting any form of complexity. We do not live in a special universe, we simply live in one that is compatible with our existence. The extraordinary fine-tuning is an illusion of probability, a selection effect on a cosmic scale. Your very ability to ponder these questions is the ultimate result of winning the ultimate cosmic lottery, being born into a reality where the numbers just happen to allow for stars, planets, and life. This idea that the universe might be fine-tuned for life finds a strange echo in a theory born from our own planet. The Gaia hypothesis proposes that Earth itself behaves like a single, living organism, a complex system where the biosphere, atmosphere, and oceans interact to maintain conditions suitable for life. Now, stretch that concept to the grandest canvas imaginable. Could the entire cosmos be a self-regulating, living entity? The laws of physics appear to be a perfect recipe for building complexity. Gravity pulls clouds of hydrogen together to forge stars, whose fiery hearts then cook heavier elements. When these stars explode, they scatter those elements across space, providing the raw materials for planets, oceans, and eventually life itself. It is a cosmic cycle that seems to foster order from chaos, moving from simple particles to complex molecules, to conscious minds that can look back and wonder at it all. This progression is not a random accident, but a direct consequence of the universe's fundamental rules. Is it possible that this drive toward complexity is the universe's way of sustaining itself, a form of cosmic metabolism? Perhaps the cosmos is not a cold, empty void, but a vast, slow-moving system with its own kind of physiology. And if a planet can achieve a form of homeostasis, could the universe itself possess a kind of awareness? This is not suggesting a god in the traditional sense, but a form of panpsychism, the idea that consciousness is a fundamental property of all matter, just like mass or charge. In this view, the universe is not conscious in the way you or I are, but it might possess a faint, diffuse form of sentience, a cosmic mind on a scale so vast we cannot perceive it. We, with our thoughts and feelings, might be tiny neural flickers within that greater mind, localized points where the universe has become aware of itself. This transforms our place in the cosmos from accidental tourists to integral components of a living, breathing, and perhaps even thinking universe. Are we merely inhabitants of this reality, or are we the universe's way of experiencing its own breathtaking existence? The idea of a conscious universe naturally leads us to a theory that challenges our deepest assumptions about awareness itself. Panpsychism proposes that consciousness is not a rare and miraculous product of complex brains, but a fundamental property woven into the very fabric of reality, as universal as mass or electrical charge. In this view, every physical entity, from a human being to an electron, possesses some form of inner experience. It might be a dim, primitive flicker for a particle, but it is a form of feeling nonetheless. This stands in stark contrast to the standard scientific view, which holds that consciousness is an emergent phenomenon. According to that model, when you arrange non-conscious matter, like atoms and molecules, into a system of sufficient complexity, like a human brain, consciousness simply pops into existence as a new property. But this leaves us with the infamous hard problem of consciousness. How exactly do objective physical processes in the brain generate subjective, first-person experience? How do the electrical and chemical dances of neurons create the rich inner world of the color red, the taste of chocolate, or the feeling of love? The emergence of experience from non-experience seems like a kind of magic, a transition that science has so far been unable to explain. Panpsychism offers an elegant, if startling, solution. If consciousness is a fundamental feature of the cosmos, then it never has to emerge. It was always there. The challenge is not to create it from nothing, but to combine it. Just as simple physical particles combine to form complex structures, simple forms of consciousness might combine to form the rich, unified awareness we experience. Think of the fundamental units of reality as each possessing a single note of experience. A quark might know only a faint hum of existence. When these particles combine into atoms, and then into molecules, and eventually into the intricate network of a brain, those countless simple notes could orchestrate themselves into the complex symphony of human consciousness. This does not mean a rock is thinking deep thoughts. Its atomic constituents are likely too disorganized to form a unified mind. But it suggests that even a rock has some minute, fragmented inner life, a silent, scattered dust of experience. The implications are profound. It means the universe is not a cold, dead void, but a vibrant, feeling place. It suggests that the spark of awareness inside you is not an alien visitor in a mechanical cosmos, but a native part of its essence, a shard of the universe's own capacity for feeling that has been concentrated and refined through billions of years of evolution. If this is true, then we are not just living in the universe, we are the universe experiencing itself in a deeply intimate and personal way. If consciousness is indeed a fundamental property of the cosmos, then the destruction of information becomes an act of cosmic vandalism. This brings us to a conflict that has shaken theoretical physics to its core, the black hole information paradox. At its heart lies a brutal contradiction between our two most successful theories. Einstein's general relativity describes black holes as simple, perfect traps. Once matter crosses the event horizon, it is gone forever. Its information, the unique arrangement of particles that made it a star, a planet, or a book, is irretrievably lost to our universe. The black hole itself remembers only the total mass, electric charge, and spin. Everything else is erased. For decades, this was accepted, if unsettling. Then Stephen Hawking applied quantum mechanics to black holes and made a startling discovery. He showed that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they slowly leak radiation, a faint whisper of particles now known as Hawking radiation. This radiation carries energy away from the black hole, causing it to gradually shrink and over eons evaporate completely. The paradox emerges from the nature of this radiation. Hawking calculated that this Hawking radiation is entirely random, purely thermal. It contains no information whatsoever about the material that fell in. So, when the black hole finally evaporates, all the information about the countless stars, planets, and atoms that ever crossed its horizon has simply vanished from reality. This is a catastrophe. Quantum mechanics is built on the unshakable principle of unitarity, which states that information is never destroyed. It can be scrambled, hidden, or transformed, but it must always, in principle, be recoverable. If you burn a book, the information seems lost in the smoke and ash, but a hypothetical superintelligence could, in theory, collect every particle of smoke, measure every photon of light, and reconstruct the entire book. Hawking's calculation suggested that black holes violate this most sacred rule of physics. They are the ultimate shredders, and the cosmic ledger can no longer balance. The theoretical world split into warring camps. One side defended Hawking, willing to rewrite quantum mechanics. The other insisted that quantum mechanics must be right, and therefore Hawking must be wrong. The search for a solution has spawned some of the most bizarre ideas in modern science. One proposal is black hole complementarity. It suggests that from the perspective of an outside observer, the information never actually falls in. Instead, it is smeared and encoded onto the event horizon itself, much like the holographic principle, and is then slowly radiated back out in a scrambled form within the Hawking radiation. However, from the perspective of an astronaut foolish enough to fall in, they would cross the horizon uneventfully, their information traveling inward to the singularity. Both perspectives are correct in their own frame, but they can never be compared, preserving the consistency of physics. This elegant idea, however, led to another shocking proposal, the firewall paradox. If information is being emitted from the horizon, then the vacuum just outside the black hole must be highly excited, a searing wall of energy that would instantly incinerate any infalling astronaut. This replaces the gentle horizon of general relativity with a violent boundary of fire. The very nature of the event horizon is at stake. Is it a placid point of no return or a lethal inferno? The most widely accepted resolution today is that Hawking was almost right, but not quite. The prevailing belief is that the information does escape, meticulously encoded in the correlations between the Hawking radiation particles. It is not in the individual particles, but in their subtle, intricate relationships, like a message hidden not in the words of a book, but in the pattern of the letters across every page. Decoding it would be a task of cosmic complexity, but the information is, in principle, there. The black hole evaporates, and the information is returned to the universe, albeit in a form so chaotic it is practically irrecoverable. The universe, it seems, keeps perfect records after all, even if its filing system is the most complex puzzle imaginable. This placid horizon, the gentle gateway of general relativity, is now threatened by a wall of fire. The black hole firewall paradox is a desperate and radical solution to the information problem, one that suggests the edge of a black hole is not a smooth transition into darkness, but a violent, lethal boundary. If information must escape a black hole to preserve quantum mechanics, then the vacuum just outside the event horizon cannot be calm. It must be a seething, high-energy state, a blistering curtain of particles that would instantly vaporize anything crossing it. An astronaut falling toward a black hole would not experience the uneventful passage predicted by Einstein, but would be obliterated in a flash of energy long before reaching the point of no return. This firewall ensures that no information ever actually falls in, sidestepping the paradox by turning the horizon into a destructive shield. Yet this solution comes at a terrible cost. It directly violates Einstein's equivalence principle, a cornerstone of general relativity which states that an observer in free fall should not feel any special effects when crossing the event horizon. For that astronaut, the horizon should be a location in space, not a physical barrier. The firewall creates a privileged, violent location, fundamentally breaking our understanding of gravity in its most extreme environment. This leaves physicists at an impasse. We must choose between violating the sacred principle of quantum information preservation or violating the foundational principles of general relativity. The firewall is a signpost pointing to a deep incompleteness in our physical theories. It screams that we are missing the final piece, a theory of quantum gravity that can seamlessly unite these two conflicting descriptions of reality. The debate over the firewall is not just about what happens at the edge of a black hole. It is a battle for the soul of physics itself, forcing us to confront which of our most cherished laws must bend and which must break to reveal the true nature of the cosmos. That paradox of the placid horizon and the searing firewall forces us to rethink the very nature of connection in the cosmos. A radical new idea suggests that the strange links of quantum physics and the cosmic tunnels of relativity are not just similar, they are one and the same. This is the ER equals EPR conjecture, a proposal that wormholes and quantum entanglement are two sides of the same coin. The name itself is a clue linking the Einstein-Rosen bridge, the formal name for a wormhole, with the Einstein-Podolsky-Rosen paradox, which describes the bizarre phenomenon of quantum entanglement. Einstein famously called entanglement spooky action at a distance, where two particles become linked in such a way that measuring one instantly influences the other, no matter how far apart they are. This seems to violate the cosmic speed limit set by light, and it deeply troubled him. But what if this spooky connection has a physical shape? The ER equals EPR idea proposes that those two entangled particles are not communicating faster than light. They are actually connected by a microscopic wormhole, a tiny bridge in the fabric of spacetime. The particles are not far apart, they are linked by the shortest path possible, a secret tunnel through the geometry of the universe. This provides a stunningly elegant solution to the paradox. There is no spooky action, just a geometric shortcut. When you measure one particle, the effect travels through this Planck-scale wormhole to its partner instantly, because the tunnel makes them neighbors in the hidden geometry of reality. This transforms our understanding of the quantum world. Every time we create a pair of entangled particles in a lab, we might be unknowingly knitting a minuscule wormhole between them, stitching the fabric of spacetime itself with a new thread. The implications for unifying general relativity and quantum mechanics are profound. For decades, these two pillars of physics have been at odds, one describing the smooth curvature of spacetime and the other the frantic, probabilistic dance of particles. But if entanglement, the quintessential quantum phenomenon, is actually built from the geometry of spacetime, then the two theories are fundamentally intertwined. Space-time itself may be a network of these quantum connections, a cosmic tapestry woven from countless threads of entanglement. The solidity of the world around us, the very distance between objects, could emerge from the density and complexity of this underlying network. This idea even offers a new perspective on black holes. Imagine two black holes that are quantum entangled. According to this conjecture, they would not be two separate objects, but the two mouths of a single giant wormhole. Falling into one black hole would not lead to a singularity, but would send you through this cosmic tunnel to emerge from the other. The interior of the black hole is not a dead end, but a bridge. This paints a picture of a universe where the deepest layers of reality are not populated by lonely particles, but by a vibrant, connected web of geometric links. The emptiness of space is an illusion. Beneath the calm surface lies a labyrinth of microscopic wormholes, each one a testament to the invisible bonds that tie the cosmos together into a single, inseparable whole. Stephen Hawking once proposed a cosmic rule so fundamental it acts as a guardian of history itself. The chronology protection conjecture suggests the laws of physics contain a built-in safety mechanism that prevents time travel to the past on any meaningful scale. Hawking essentially argued that the universe seems to abhor a paradox. The classic example is the grandfather paradox. If you were to travel back in time and prevent your own grandfather from meeting your grandmother, you would create an impossible logical loop. Your own birth would never have happened, making your time travel journey impossible in the first place. Such a contradiction cannot be allowed in a consistent reality. But how does the universe enforce this rule? The mechanism is not a mystical force, but a physical one. Consider the theoretical pathways to the past like a wormhole time machine. To transform a wormhole into a time machine, you would need to create a closed time-like curve, a path through space-time that loops back on itself. One proposed method involves taking one mouth of a wormhole and moving it at near light speed or placing it near an intense gravitational field. Time dilation would cause that end to age slower than the stationary end. If you then brought the two mouths together, a traveler could jump into the moving mouth and exit the stationary one at a moment before they even entered. Yet Hawking postulated that the very act of creating this loop would trigger its own destruction. The vacuum around the wormhole would become unstable. As virtual particles travel through the time loop, they could complete an infinite number of circuits, their energy building upon itself in a runaway feedback effect. This would create an infinite energy density at the threshold of the closed time-like curve, a cataclysm that would either destroy the wormhole instantly or collapse it into a black hole before any macroscopic object, like a human being, could ever pass through. The universe protects its own chronological order with a firewall of physics, ensuring that the past remains immutable and paradoxes remain the stuff of fiction, not physical reality. This demonstrated quantum phenomenon reveals a startling secret about the void. The Casimir effect shows us that empty space is not empty at all. Picture two flawless, uncharged metal plates placed incredibly close together in a perfect vacuum, separated by a gap smaller than the width of a human hair. According to classical physics, nothing should happen, but in the quantum world, something extraordinary occurs. The space between the plates restricts the kinds of virtual particles that can flicker into existence, while the space outside the plates allows for a much wider spectrum. Virtual particle pairs, matter and antimatter, are constantly borrowing energy from the vacuum and annihilating each other to pay it back, all within a time frame permitted by quantum uncertainty. With more activity outside the plates than between them, a subtle pressure pushes the plates together. It is an invisible, irresistible force born directly from the seething energy of nothingness. This is the zero-point energy of the vacuum, a background hum of activity that permeates every cubic centimeter of the cosmos. This energy is not zero. The void is alive. This discovery forces a profound question. If empty space contains this inherent energy, Could it be the source of the mysterious repulsive force accelerating the expansion of the universe? The cosmological constant, the leading candidate for dark energy, is exactly this, the energy density of the vacuum itself. The puzzle is one of scale. When physicists calculate the theoretical value of this vacuum energy based on quantum mechanics, the number is outrageously, catastrophically large. It should be 120 orders of magnitude stronger than what we observe. If the vacuum energy were that powerful, the repulsive force would have ripped apart atoms, stars, and galaxies before they ever had a chance to form. The fact that we exist means the observed value of dark energy is almost zero, but not quite. Why is the energy of the void so finely tuned to allow for our existence? This leads to a tantalizing, almost science fiction possibility. If we can harness the Casimir effect, could we someday extract useful energy from the vacuum of space itself? The idea of free energy from nothing is the ultimate dream, but the reality is immensely challenging. The energy is everywhere, but it is locked in a state of perfect equilibrium, like an ocean at perfect rest. To extract it, you would need to break that symmetry, to create a kind of quantum paddle that can dip into this sea and draw power out. Some theoretical designs suggest that rapidly oscillating Casimir cavities could achieve this, essentially tricking the vacuum into giving up some of its boundless energy. For now, this remains a theoretical frontier, a whisper of a future technology that could tap into the fundamental hum of reality. The gentle push of two metal plates is a tiny, laboratory-scale testament to the unimaginable power latent in the silent emptiness all around us. Every electron in the cosmos is a perfect copy of every other, a uniformity so exact it defies simple chance. The physicist John Wheeler once proposed a breathtakingly simple explanation for this cosmic sameness, a theory known as the one-electron universe. He suggested that there is not a sea of countless identical electrons, but only a single one. This lone entity is weaving its way forward and backward in time, tracing a complex, tangled path through all of existence. Every time it moves forward, we observe it as an electron. When it reverses its course through time, we perceive it as its antimatter counterpart, a positron. In this radical view, the entire universe is embroidered from the world line of one fundamental thread. This elegant idea would naturally account for the perfect uniformity of all electrons because they are all the same particle, just encountered at different points along its immense zigzagging timeline. It also offers a poetic explanation for antimatter, framing it not as a separate substance, but as ordinary matter traveling backward in time. Imagine the entire history of the cosmos as an immense tangled ball of yarn. The single electron is a needle stitching in and out of the temporal fabric. When the needle moves forward, it creates what we call an electron. When it pulls backward, it leaves the impression of a positron. Every particle interaction, from the fusion in the heart of a star to the electrical impulses in your brain, is just a different point where this solitary traveler changes its temporal direction. The sheer number of electrons we observe is not a count of different objects, but a measure of how many times this one entity has crossed our present moment. While profoundly beautiful, the theory faces significant hurdles. It struggles to explain why we see so many more electrons than positrons in the universe, a fundamental asymmetry that would require an overwhelming bias for forward time travel. Modern particle physics also describes other particles like quarks and neutrinos, which would presumably require their own solitary time travelers, complicating the elegant simplicity of the original idea. Yet, even as a speculative thought experiment, the one-electron universe leaves us with a powerful legacy. It challenges our deepest assumptions about identity and the arrow of time, suggesting that the cosmos might be far more interconnected and economical than we ever dreamed. The next time you use a device powered by electricity, consider the possibility that the very same electron moving through the circuit has also been part of every star, every living thing, and every moment in history, a solitary dancer in the infinite ballroom of time. The universe is written in two conflicting languages. One describes the vast cosmic dance of gravity, the other the frantic quantum jitter of particles. For over a century, these two dialects have refused to speak to one another, creating a schism at the very heart of physics. The ultimate goal, the holy grail of science, is to find a single, elegant framework that can translate both into one unified tongue. This is the quest for a theory of everything. It would be a single set of equations capable of describing every force, every particle, and every interaction in the cosmos, from the furious birth of the Big Bang to the gentle fall of an apple. The two most prominent contenders in this epic struggle are string theory and loop quantum gravity. String theory, as we have explored, proposes that the fundamental ingredients of reality are tiny, vibrating strings, with their different harmonies producing every particle and force, including gravity. Its great appeal is its comprehensiveness, offering a potential blueprint for the entire universe. Yet it requires those extra, hidden dimensions and so far remains stubbornly untestable. Loop quantum gravity takes a different, more minimalist approach. It suggests that space itself is not a smooth background, but is woven from a fabric of tiny, indivisible loops. This theory beautifully banishes the infinities of singularities, replacing the Big Bang with a big bounce, but it struggles to incorporate the other fundamental forces with the same ease. The challenge is not just mathematical, it is philosophical. Is our universe fundamentally made of strings vibrating within space, or is it a web of interconnected loops that themselves define space? Or is the truth something entirely different, a third perspective we have not yet conceived? The difficulty is staggering. To probe the energies where these theories become relevant, we would need a particle accelerator larger than our entire solar system. We are like sailors trying to map an ocean by studying the waves from a small pond. Finding such a theory would represent the culmination of centuries of scientific progress, a moment where human curiosity finally deciphers the deepest code of reality. It would answer questions about the origin of the universe, the nature of time, and the fate of existence itself. But this quest raises a humbling, almost terrifying question. Is the human mind a product of biological evolution on a single, tiny planet, even equipped to comprehend the ultimate laws of the cosmos? Our brains are wired for survival in a middle world of medium-sized objects and slow speeds. The bizarre, counterintuitive realms of the quantum and the cosmic may be as incomprehensible to us as a symphony is to a bacterium. The universe may be built on a logic so alien that our very tools of reason are inadequate to grasp it. The search for a theory of everything is therefore more than a scientific endeavor. It is a test of whether we can truly know the home we live in, or if we are forever destined to see only its shadows. The elegant equations of string theory promise a theory of everything, but they deliver a puzzle of infinite possibilities. Instead of a single, unique universe, the mathematics reveals a staggering landscape of potential realities, each with its own distinct set of physical laws. This cosmic terrain is populated by the different ways those tiny extra dimensions can curl up, with each possible configuration yielding a different universe with different particle masses and force strengths. In this picture, our universe is not special or inevitable. It is simply one valley in an endless mountain range of possibilities, a place where the constants are just right for stars, planets, and life to form. This string theory landscape provides a powerful physical basis for the multiverse and a concrete answer to the puzzle of fine-tuning. We do not live in a universe designed for life. We live in one of the rare, habitable corners of a vast and mostly barren cosmic archipelago. This elegant solution, however, comes with a profound cost. If every possible universe exists within the landscape, then string theory may have surrendered its power to make specific, testable predictions for our own world. We can no longer ask why the electron has its specific mass, because in the grand landscape, it has every possible mass somewhere. The theory explains everything by predicting everything, which to critics is the same as predicting nothing at all. It raises a disturbing question for the future of fundamental physics. Are we discovering the unique laws of reality, or are we merely mapping the local bylaws of our own accidental cosmic neighborhood? The search for a final theory becomes a journey into a library containing every book that could ever be written, leaving us to wonder if the ultimate story of our universe is just one sentence in an infinite, unreadable text. Our own cosmic home might be the interior of a colossal black hole. This is the startling proposal of the black hole universe theory, a model that reimagines the Big Bang as the violent formation of our prison walls. In this view, the singularity that birthed our cosmos was not a unique event in absolute nothingness, but the moment a massive object collapsed into a black hole within a much larger parent universe. As matter was crushed to an unimaginable density, the event horizon formed around it, and we have been living inside that boundary ever since. The three-dimensional space we know and measure could be the interior surface of this cosmic trap, a reality projected from information stored at its edge, much like the holographic principle suggests. The force we perceive as dark energy, the mysterious driver of cosmic acceleration, could simply be the effect of this boundary continuously stretching and evolving. The expansion of our universe would not be an explosion from a point, but the ongoing growth of the black hole's interior volume as it consumes more energy and matter from the parent cosmos. This consumption could be nearly imperceptible to us, manifesting as the steady creation of new space within our reality. Imagine a fish born in a pond that is slowly but constantly being filled with more water. The fish would observe its world expanding in all directions, never realizing it is actually contained within a much larger system. For us, every new galaxy that forms at the edge of our observable universe could be a reflection of new material falling through the horizon from outside. This idea even offers a potential escape route for the information that seems to vanish into black holes. If our universe is a black hole, then the matter that falls into the black holes within our own cosmos might not be lost forever. Instead, it could be funneled through a tunnel in space-time, a wormhole, and expelled through a white hole into a brand new baby universe of its own. In this breathtakingly cyclic vision, every black hole is a potential Big Bang for a new reality. The collapse of a star in our sky could be the genesis of an entire cosmos, with its own laws of physics and its own story of cosmic evolution. We are left to wonder if the grand cycle of birth and death we see in the stars is merely a small part of an infinite fractal cascade of universes, each one a single bubble in an endless foam of existence. The cosmos is expanding toward a final, frozen silence. This is the Big Freeze, the universe's most probable end, where the relentless work of entropy achieves its ultimate victory. Entropy is simply the measure of disorder in a system, and the universe is on a one-way trip from the ordered energy of the Big Bang to a state of maximum useless chaos. Imagine a hot cup of coffee left alone in a vast room. It will inevitably cool, its heat spreading out evenly into the surrounding air until everything is the same lukewarm temperature. No more energy can be extracted from this uniform state. The cosmic coffee will never spontaneously heat up again. This is the heat death of the universe. The engine of existence is slowly running down. First, the stars will vanish. Over trillions of years, the last reserves of hydrogen will be exhausted, and the final star will flicker out. The galaxies will plunge into perpetual darkness. Next, even the remnants will decay. Planets will be ripped from their dead suns by rare gravitational encounters, and the very protons and neutrons that make up all matter may eventually fall apart, dissolving into a thin, expanding sea of radiation and elementary particles. Black holes, the last bastions of structure, are not eternal. Through Hawking radiation, they will slowly evaporate over unimaginable eons, vanishing in a final, faint puff of energy. The end result is a cosmos that is utterly dark, cold, and empty. There are no more temperature differences, no more energy gradients, no more structures of any kind. The universe becomes a static, featureless void, having reached a state of equilibrium where nothing ever happens again. Time itself may lose all meaning, as there are no longer any events to mark its passage. This stands in stark contrast to other proposed endings. The Big Crunch, a dramatic reversal of the Big Bang, would see the universe collapse back into a fiery singularity, a potential rebirth. The Big Rip, driven by an ever-strengthening dark energy, would see the fabric of space-time itself torn apart, shredding galaxies, stars, and even atoms in a final, violent instant. The Big Freeze is different. It is not a dramatic explosion or a collapse, but a slow, quiet fading. It is the universe dying not with a bang, but with a whimper that echoes for eternity. The existential weight of this conclusion is profound. It suggests that all of cosmic history, the birth of stars, the formation of planets, the rise of life, and the spark of consciousness, is merely a temporary, flickering rebellion against the inevitable tide of disorder. Every story ever told, every love ever felt, every great civilization built, is destined to be erased without a trace, lost in an infinite, silent, and forgetful dark. The Big Freeze is a slow, quiet surrender to entropy, but the cosmos might instead choose a far more violent exit. The Big Rip is a cosmic apocalypse driven by dark energy's ultimate victory, a scenario where its repulsive force does not just push galaxies apart, but actively tears the fabric of reality to pieces. For this to happen, dark energy must be a specific, terrifying form known as phantom energy. Unlike a constant cosmological constant, phantom energy is an anti-gravitational force that grows stronger and denser over time. As the universe expands and creates more space, the power of this phantom field intensifies like a fire that burns hotter the more it spreads. The acceleration would not just continue, it would skyrocket. At first, the effects would be subtle, lost in the vast scales of intergalactic space, but the countdown to destruction would have already begun. The first casualty would be the cosmic web itself. The gravitational glue holding galaxy clusters together would be overpowered. You would see constellations, those familiar patterns in the sky, begin to distort and then vanish as their member galaxies are flung into the ever-darkening void. Next, the phantom energy's grip would tighten on individual galaxies. The Milky Way would be torn asunder. The spiral arms, vast collections of billions of stars, would be ripped away from the galactic core. Stars would be scattered like dust in a hurricane, their orderly orbits shattered by a force stronger than gravity itself. Our solar system would be flung into the absolute blackness of intergalactic space. But the end is not yet. The phantom force would then target the solar system. The sun's gravity would no longer be enough to hold its planets. Earth would be ripped from its orbit, becoming a lone, frozen wanderer in the void. Then the sun itself would be torn apart, its nuclear furnace extinguished as the forces binding its massive plasma body together are overwhelmed. In the final moments, the phantom energy would reach down to the smallest scales. The planet you stand on would be shredded. The rocks, the mountains, the oceans, all would fly apart. Then, the very molecules that make up your body would be dissociated. The atoms themselves would be ripped open, their nuclei torn from the embrace of their electrons. Finally, space-time itself, the very stage upon which the universe plays out, would be fractured. The fundamental bonds that give reality its structure would snap. In an instant, the cosmos would cease to be a coherent universe, dissolving into a chaotic, disconnected froth of particles and broken forces. The end would not be a slow fading, but a catastrophic, instantaneous unraveling of everything that ever was. Before the discovery of dark energy, the cosmos seemed destined for a spectacular collapse. This is the theory of the Big Crunch, a once dominant vision of the universe's end where the relentless pull of gravity finally overcomes the momentum of the Big Bang. After expanding for billions of years, the collective attraction of every galaxy, star, and speck of dust would begin to slow the cosmic expansion to a halt. Then the great reversal would begin. The universe would start to fall in on itself, gaining speed as it rushed toward its own center. Galaxies, once flying apart, would begin to rush together, their light blue shifting as they converge. The background temperature of the cosmos, now just a few degrees above absolute zero, would begin to climb. As the collapse accelerates, the night sky would grow brighter and hotter, eventually glowing with the light of a billion stars crammed into an ever-shrinking volume. The end would be a mirror image of the beginning, a fiery convergence into a state of unimaginable heat and density, a singularity from which nothing could escape. This cosmic implosion was not seen as a final end, but as a potential reset button for reality. Some models suggested that this singularity might not be a terminal point, but a bounce, a moment of supreme density where the universe rebounds in a new Big Bang, giving rise to a fresh cosmos in an endless cycle of expansion and contraction. Our universe could be just one breath in an eternal cosmic rhythm, with all its history, its stars, and its life being periodically gathered back into the forge to be remade. The discovery of dark energy and the accelerating expansion dramatically reduced the likelihood of this dramatic finale. How can the universe collapse if it is flying apart faster and faster? Yet the door to the Big Crunch is not completely closed. Our understanding of dark energy is still provisional. If this mysterious force is not a constant, but a dynamic field that weakens over time or even reverses to become an attractive force, then gravity could ultimately win the cosmic tug of war. The Great Expansion could still slow, halt, and reverse, leading the universe on a long journey back to the fire. The fate of everything may depend on a battle between two invisible giants, the relentless pull of gravity from all that exists, and the mysterious, repulsive push of the vacuum itself. That seemingly empty space around you holds a terrifying secret. It might be a cosmic house of cards balanced in a temporary state that could collapse at any moment. This is the theory of vacuum metastability, and it suggests our entire universe is living on borrowed time. We assume the vacuum of space is a true and stable nothingness, its energy at an absolute minimum. But what if our vacuum is merely metastable, like a ball resting in a small dip on the side of a much larger valley? It seems stable for now, but a single nudge could send it rolling down into the true, deepest valley, the state of lowest possible energy. In the quantum world, that nudge is always possible. Through a process called quantum tunneling, a tiny region of space could spontaneously transition into this true vacuum. Think of it as a bubble of a fundamentally new reality suddenly popping into existence. The laws of physics inside this bubble would be entirely different. The strength of gravity, the nature of light, the very rules that allow atoms to bind together, all of it would be rewritten in an instant. This bubble would then expand in all directions at the speed of light, its wall a wave of absolute annihilation. There would be no warning. One moment, the universe would be as it is. The next, a sphere of obliteration would be racing toward us, and by the time we could see its light, it would already be upon us. The wall of true vacuum would not crush or burn what it touches. It would simply erase the old laws of physics, dissolving every atom, every force, and the very fabric of spacetime itself, replacing it with a new reality where structures like planets, stars, and life are likely impossible. The entire cosmos as we know it would be permanently erased. The most chilling part is that this event could be triggered anywhere at any time by a random quantum fluctuation. It could have already happened in a distant galaxy, and the sphere of doom could be on its way right now, completely undetectable until it arrives. our seemingly solid and reliable universe might be the most fragile thing of all, a beautiful, temporary configuration waiting for a single, random quantum event to bring it all crashing down. The ghostly pull of dark matter might not come from clouds of exotic particles at all. Some of that invisible mass could be lurking in the form of ancient, primordial black holes. These are not the stellar corpses we know, born from the collapse of massive stars. They are relics from the universe's first chaotic moments, forged directly in the searing heat of the Big Bang. In that initial furnace, extreme density fluctuations could have caused pockets of space to collapse under their own gravity, condensing directly into black holes of almost any size. A region with the mass of a mountain might have crumpled into a black hole no wider than an atom, while another with the mass of a star could have formed one as wide as a city. These primordial objects would have been scattered throughout the cosmos long before the first star ever flickered on, seeding the darkness with their immense hidden gravity. This elegant idea bridges the vast scales of cosmology and the bizarre rules of the quantum world. For the smallest of these black holes, their formation and potential evaporation through Hawking radiation are purely quantum gravitational events. Their existence would be a direct window into the physics of the universe's first second. The hunt for these cosmic fossils is now on, with astronomers searching for them across a staggering range of masses. On the smaller end, they could explain the mysterious nature of dark matter. If countless asteroid-mass primordial black holes drift through our galaxy, their collective gravity would perfectly mimic the dark matter halos we infer. To find them, scientists watch for the telltale flash of a microlensing event when one of these dark objects passes in front of a distant star. Its gravity acts as a lens, bending the starlight and causing the star to temporarily brighten. We have not found enough of these events to account for all dark matter, but the search continues, probing different mass ranges. At the other extreme, some theories suggest that the supermassive black holes anchoring the centers of galaxies, weighing millions of solar masses, were not built slowly over time. They could have been born that way as primordial giants that simply started with a head start, providing the initial gravitational seeds around which entire galaxies coalesced. Discovering a primordial black hole would be a revolution. It would solve the dark matter puzzle with known physics, eliminating the need for undiscovered particles. It would confirm a dramatic new picture of the Big Bang's chaotic infancy, and it would hand us a natural laboratory for studying quantum gravity. The entire history of the cosmos might be written not in invisible particles, but in the silent, ancient darkness of these primordial traps. The cosmos has not always been accepted as a story with a definitive beginning. For much of the 20th century, a powerful and elegant rival challenged the very idea of a Big Bang, arguing instead for an eternal, unchanging universe. This was the steady-state theory, a model that proposed the cosmos had no start and will have no end. It described a universe eternally expanding, but to avoid thinning out into nothingness, it postulated the continuous, spontaneous creation of new matter. A few hydrogen atoms were thought to pop into existence in every cubic meter of space every few billion years, just enough to maintain a constant average density as the galaxies drifted apart. In this vision, the universe was forever renewing itself, looking much the same at any point in its infinite past or future. It was a profoundly comforting idea, a cosmos without birth pangs or a final death, an endless, self-sustaining cycle. The discovery of the cosmic microwave background radiation, the cooled remnant of the universe's fiery infancy, ultimately proved to be the theory's undoing. That faint hiss of ancient light filling all of space was the predicted afterglow of a hot, dense beginning, a relic the steady state could not adequately explain. While the evidence firmly supports a dynamic cosmos with a definite origin, we must appreciate the crucial role the steady state played. It was a beautiful, bold idea that forced cosmologists to sharpen their arguments and seek definitive proof, driving the scientific process forward in its relentless pursuit of truth. But what if the cosmic speed limit itself has changed? The speed of light is the universe's ultimate constant, a fixed number woven into the very fabric of physics. Yet a radical theory suggests this is not the case, that light once traveled far faster in the universe's fiery youth. This is the variable speed of light hypothesis, a proposal that the value of c was not always 299 million meters per second. In the first moments after the Big Bang, light may have raced across the cosmos at speeds we can scarcely imagine. Why would anyone challenge such a bedrock of modern science? The motivation lies in solving some of cosmology's most stubborn puzzles, like the horizon problem. How did distant, disconnected regions of the early universe manage to reach the exact same temperature? Under the Standard Model, there simply hasn't been enough time since the beginning for light or heat to have traveled between them to establish this thermal equilibrium. It is as if 100 people in a massive, dark field all decided to light identical candles at the same instant without ever speaking. Cosmic inflation solves this by proposing the universe expanded faster than light, briefly connecting those distant regions. But the variable speed of light offers a different, equally elegant solution. If light itself moved exponentially faster in the beginning, then those distant regions could have easily exchanged energy and information, reaching a uniform temperature long before the cosmos expanded to its current scale. The entire observable universe could have been in casual contact, effectively chatting with itself, because the messenger, light, was unimaginably swift. This single change to a fundamental constant could neatly replace the need for an inflationary epoch, rewriting our story of the universe's first moments. The theory remains highly controversial, firmly outside the mainstream. Critics point out that tampering with the speed of light has cascading consequences, potentially unraveling the delicate tapestry of physics we have so carefully woven. The constancy of c is the cornerstone of Einstein's special relativity, and altering it challenges our understanding of causality, energy, and the very flow of time. Why then even entertain such a disruptive idea? Its true value may not be in being right, but in the profound questions it forces us to ask. Why are the constants of nature constant? Are they truly immutable, or could they be frozen relics from a more dynamic and violent phase of cosmic evolution? By daring to question our most basic assumptions, we probe the deepest layers of reality, ensuring that our map of the universe is drawn from curiosity, not just from convention. A revolutionary engine promised to rewrite the laws of physics from the ground up. The M-drive, or electromagnetic drive, was a concept that captivated engineers and science fiction fans alike. It was a simple, sealed metal cavity shaped like a cone. When you pumped it full of microwaves, the inventors claimed it produced a tiny, persistent thrust, pushing itself forward without expelling any propellant whatsoever. This was like sitting inside a car, pushing on the steering wheel and expecting the entire vehicle to move. It directly challenged Newton's third law, the fundamental principle that for every action there is an equal and opposite reaction. Rockets work by throwing mass backward to go forward. The M-drive claimed to generate forward momentum from nothing but bouncing microwaves in a can. The implications were staggering. It hinted at a way to manipulate inertia itself, a technology that could power spacecraft across the solar system without fuel, cutting journey times from years to months. The dream was a silent, efficient engine that could take us to Mars and beyond, forever changing our place in the cosmos. For years, a handful of research teams, including one at NASA Eagleworks Laboratory, reported measuring this elusive thrust. Their results were minuscule, a force equivalent to the weight of a single grain of sand. But in the vacuum of space, such a gentle, continuous push could theoretically build up to incredible speeds over time. The scientific community, however, was deeply skeptical from the start. The proposed explanations for how it could work bordered on the magical, invoking esoteric concepts from quantum theory that seemed more like hand-waving than solid physics. The central problem was conservation of momentum. If the drive was pushing itself forward, what was it pushing against? The microwaves bouncing inside were a closed system. The law of conservation of momentum is not just a suggestion. It is a cornerstone of our understanding of the universe, woven into the fabric of reality from the subatomic to the galactic scale. To accept the M drive was to accept that this cornerstone was crumbling. The subsequent, more rigorous investigations began to unravel the miracle. When other labs attempted to replicate the experiment, they either found nothing or discovered subtle, overlooked sources of error. The most likely culprit was experimental bias and thermal effects. As the resonant cavity heated up from the intense microwaves, it expanded minutely. This thermal expansion could interact with the measuring apparatus or even with the Earth's magnetic field, creating a false signal that looked exactly like thrust. In one crucial test, researchers mounted an M drive in a vacuum chamber on a pendulum designed to be exquisitely sensitive to any force. They ran the test and the device appeared to push forward. Then they rotated the entire setup by 180 degrees. If the thrust was genuine, it should have reversed direction. It did not. The push remained in the same orientation, proving it was not generated by the drive itself, but by an external interaction, most likely with the laboratory's magnetic environment. The scientific consensus today is clear: the M drive does not work. It was a compelling illusion, a phantom thrust born from our own desire for a breakthrough. Yet its story is far from a failure. It stands as a powerful lesson in the essential, often painful, self-correcting mechanism of science. The allure of a world-changing discovery can be so strong that it clouds judgment, even among brilliant researchers. The M drive episode highlights the critical importance of blinding experiments, of rigorous controls, and of the scientific community's collective duty to challenge extraordinary claims. It reminds us that the universe is under no obligation to conform to our wishes, no matter how noble they may be. The true engine of progress is not wishful thinking, but the relentless, meticulous, and sometimes disappointing pursuit of evidence, no matter where it leads. The profound silence of the cosmos is a scream into an apparently empty theater. We gaze at a universe containing trillions of stars with billions of potentially habitable planets, a cosmos that has had over 13 billion years to spawn intelligent life. The numbers alone suggest a galaxy teeming with civilizations, yet when we listen, we hear nothing but the natural hum of celestial bodies. This staggering contradiction between the high probability of alien life and the utter lack of any evidence for it is the Fermi Paradox, a mystery that forces us to question not just our place in the universe, but the very nature of life and intelligence itself. One of the most unsettling solutions is the Great Filter. This theory posits that there exists a barrier, a nearly insurmountable challenge, that prevents life from progressing to a stage where it can colonize the stars. The terrifying question is not whether the filter exists, but where it lies on the timeline of development. Is it behind us, a hurdle we have already passed? Perhaps the emergence of life itself from non-living chemistry is astronomically rare, or the leap from single-celled to complex, multicellular organisms is the true miracle. If so, we are the lucky ones, the winners of a cosmic lottery that most other worlds lose. The more chilling possibility is that the Great Filter still lies ahead of us. It could be that almost every civilization that reaches our level of technological development inevitably discovers something that leads to its own destruction. This could be the invention of artificial intelligence that turns against its creators, nuclear annihilation, a genetically engineered plague, or some technological catastrophe we have not yet even conceived. In this scenario, the silence of the universe is a graveyard, a warning of a fate that awaits all who rise to a certain level of power. Another compelling idea is the zoo hypothesis. This suggests that we are not alone, but are living in a kind of cosmic wildlife preserve. Advanced civilizations are aware of us, but have chosen a strict policy of non-interference, allowing humanity to develop naturally without outside influence, much like scientists observing animals in their natural habitat. They are watching, but they are hidden, their technology so advanced that they can remain completely undetectable to our primitive senses. This would explain the silence without requiring a grim, self-destructive filter. Perhaps first contact is a rite of passage, reserved only for when a species proves it is mature enough to handle the knowledge and responsibility. Other answers are equally thought-provoking. Perhaps spacefaring civilizations are common, but the vast distances and timescales of the galaxy mean that their signals and visits are simply too brief or too infrequent for us to have noticed yet. We might be like a lone island in a vast ocean with ships passing too far away to see. Or maybe the universe is simply too dangerous, filled with predatory civilizations that force everyone else into radio silence for their own survival. The most existential possibility is that we are truly the first, that the conditions for intelligent life have only recently fallen into place in cosmic history, and we are the pioneers. The Fermi Paradox holds up a mirror to humanity, forcing us to confront our own fragility and potential. Are we a fleeting, self-extinguishing flash in the cosmic night, or are we on the cusp of joining a silent, ancient community of starfaring beings? The answer to where everybody is may ultimately determine whether our future is among the stars or confined forever to the quiet solitude of our own world. That profound silence is not for a lack of trying to quantify it. A single equation scrawled on a chalkboard in 1961 attempts to bridge the gap between the vast numbers of the cosmos and the eerie quiet. The Drake equation is not a recipe for an answer, but a structured way to frame our ignorance. It is a chain of probabilities, multiplying together a series of factors to estimate the number of civilizations in our galaxy with which we might actually communicate. The equation begins with the grand and the certain, the number of stars forming each year in the Milky Way. We can observe this, then it narrows step by step into the realm of the unknown. What fraction of those stars have planets? We now know this number is high, with most stars hosting planetary systems. Then, how many of those planets are habitable, orbiting in the Goldilocks zone where liquid water could exist? This, too, seems promising, with rocky planets discovered in this zone around many stars. The next factors are where the certainty evaporates and the true mystery begins. What fraction of those habitable worlds actually develop life? We have a single data point, Earth, but is life a cosmic imperative, emerging wherever conditions are right, or a freak accident of chemistry? Then, if life does arise, what fraction evolves into intelligent, tool-using species? Intelligence is not an inevitable endpoint of evolution. It might be a rare and quirky survival strategy. The final factors are the most sobering. What fraction of intelligent civilizations develop the technology to broadcast their presence across the stars? And perhaps most crucially, how long do those civilizations last? A communicative civilization might only have a brief window, a few centuries perhaps, between inventing radio and succumbing to self-destruction or some other existential threat. The product of all these numbers, some nearly 1, others potentially infinitesimally small, yields n, the number of detectable civilizations. Depending on your optimism, n could be in the thousands or it could be exactly 1. This equation is the mathematical heart of the search for extraterrestrial intelligence, the SETI program. For decades, radio telescopes have been patiently scanning the sky, listening for a signal that stands out from the natural cosmic static, a deliberate hello or an accidental leak of another world's technology. Finding even a single such signal would be the most profound discovery in human history. It would mean we are not a solitary fluke. the laws of physics and biology would have produced company elsewhere. The entire universe would transform from a collection of objects into a potential community. Every star in the night sky would become a possible harbor for another story, another perspective on reality. The silence of the Fermi Paradox would be broken, replaced by a single, powerful voice telling us we are not alone in the dark. Yet that profound silence might be the only honest answer. The rare Earth hypothesis presents a sobering counter-argument to cosmic optimism, suggesting that the vibrant, complex life on our planet is not a common outcome, but a cosmic jackpot of almost impossible odds. It is not enough for a world to be merely in the habitable zone. The emergence of animals, let alone intelligent beings, requires a chain of geological and astrophysical luck so long and fragile that we might truly be alone in the galaxy. Consider our large moon. It was born from a cataclysmic collision with a Mars-sized object in the early solar system, a violent accident that gave Earth a lunar partner far larger than any other moon relative to its planet. This massive satellite acts as a gravitational anchor, stabilizing our world's axial tilt over billions of years. Without the moon's steadying hand, Earth's poles would wander chaotically, causing wild, unpredictable climate swings that would prevent the long-term, stable environments necessary for complex life to evolve. Our planet's geology is another stroke of fortune. Earth's active plate tectonics act as a global planetary thermostat. As tectonic plates slide and sink, they recycle carbon from the atmosphere into the mantle and back out through volcanoes. This colossal, slow-moving cycle regulates global temperatures, preventing a runaway greenhouse effect or a permanent global ice age. A world without this geological recycling could easily become either a scorching hellscape like Venus or a frozen snowball. Then there is our celestial guardian, Jupiter. This gas giant, with its immense gravity, acts as a cosmic vacuum cleaner for the inner solar system. It deflects or captures countless comets and asteroids that would otherwise bombard our world with extinction-level impacts. While some early impacts may have delivered the water and organic compounds essential for life, a constant, heavy bombardment would prevent life from ever gaining a foothold. A solar system without a Jupiter-like sentinel might see its inner planets perpetually pummeled, sterilizing any nascent biology. Each of these factors is a Goldilocks condition in itself, not too much, not too little, but just right. And the list extends further, a right kind of star that is stable and long-lived, a magnetic field strong enough to shield the surface from lethal stellar radiation, and the sheer timing of evolutionary leaps that led from single cells to conscious minds. When you multiply all these low probabilities together, the number of Earth-like worlds with Earth-like life could plummet from billions to just one. We may not be looking out at a silent galaxy empty of life, but at one where the overwhelming majority of life is simple, microbial, and trapped forever in its planetary pond. The silence is not a paradox, but a reflection of our own profound rarity. We are not hidden in a crowd, we are a solitary voice in a cathedral of unimaginable scale, and the echo we keep waiting for may never come. The building blocks of life are not confined to our planet. They are scattered throughout the cosmos, woven into the fabric of comets and hidden within ancient asteroids. The panspermia hypothesis proposes a radical idea that life itself, or at least its essential ingredients, is a cosmic traveler. It suggests that microorganisms or complex organic compounds can hitch a ride on space rocks, seeding life on any world with the right conditions. We may all be descendants of interstellar wanderers. The evidence for this is mounting from two very different frontiers. Here on Earth, we have discovered extremophiles, tenacious life forms thriving in places once thought utterly sterile. These microbes flourish in boiling acid, in the crushing pressures of the deep ocean, and even frozen solid in Antarctic ice. Their existence proves that life is far more robust than we ever imagined, capable of surviving journeys that would be lethal to most creatures. If a microbe can slumber inside a glacier for millions of years, could it not also hibernate within the protective interior of a meteoroid, shielded from radiation during a long voyage between worlds? Meanwhile, our telescopes and space probes have detected a rich chemistry in the void. Complex organic molecules, the precursors to life, are found in vast clouds of interstellar gas on the surfaces of asteroids and within the icy nuclei of comets. Amino acids, the very letters in the alphabet of life, have been discovered in meteorites that fell to Earth. The universe appears to be preloaded with life's raw materials, a cosmic soup waiting for a warm planetary kitchen to begin cooking. This leads to a staggering possibility. The spark that ignited life on our young planet 4 billion years ago may not have been a local event. It could have arrived from the skies, a gift from a distant star system delivered by a comet's icy embrace. A single hardy bacterium, protected within a Martian rock blasted into space by an ancient impact, could have drifted for eons before tumbling through our atmosphere and finding a new home in Earth's primordial oceans. In this scenario, we are not truly Earthlings, but the children of the galaxy. Our ancestry stretches back to another world, another sun. Every living thing on this planet, from the tallest tree to the smallest insect, would share a lineage that began somewhere else in the cosmos. We are not merely inhabitants of the universe, we are a part of it that has become self-aware, a local expression of a potentially universal biological imperative. Are we the original garden, or just one fertile field in an infinite, interconnected landscape of life? The quantum world is a sea of shimmering possibilities, yet we only ever perceive a single, solid shore. This is the core of the measurement problem, the baffling gap between the blurry quantum realm and our definite everyday experience. A compelling solution suggests that reality itself is shaped by a process of cosmic selection. Quantum Darwinism proposes that the classical world we see is not chosen by a conscious observer, but by the environment itself, acting as a ruthless editor. In the quantum arena, countless superpositions exist simultaneously. An electron is both here and there. A particle exists in a haze of potential locations. But when this quantum system interacts with its environment, whether through air molecules, photons of light, or even background radiation, something profound happens. Most of these fragile quantum states are too delicate to survive. They are erased like whispers drowned out by a crowd. Only the most robust, stable states can withstand the constant bombardment and be copied over and over again into the environment. This is the quantum version of natural selection. Think of a jungle filled with countless species. Only those with traits that allow them to effectively reproduce and spread their genetic information will come to dominate the ecosystem. In the same way, only certain quantum states are fit enough to be widely copied and proliferated. The environment acts as a communication channel, broadcasting the information about these select states. You perceive a table as solid and in one place because that particular state of the table's particles has been massively replicated and imprinted onto trillions of photons bouncing off it, which then travel to your eyes. The other potential states, the ghostly versions of the table existing elsewhere, were simply not stable enough to leave so many copies. They were selected against. Your consciousness is not doing the collapsing. It is simply reading the news that the environment has already printed in bold, repeating headlines. What you experience as objective reality is just the consensus formed by this relentless process of information proliferation. The universe, in its constant interactions, favors the stable and the communicable, winnowing the infinite quantum possibilities down to the singular, classical world we all agree upon. Those quantum waves we perceive moving forward might also be echoing back from the future. The transactional interpretation of quantum mechanics offers this startlingly symmetrical view, proposing that every quantum event is a negotiation across time itself. When an electron is emitted from a source, it does not simply travel as a lone wave to a detector. According to this theory, the event begins with what is called a retarded wave, the standard alpha wave that moves forward in time from the point of emission. But upon reaching a potential destination, like a screen in the famous double-slit experiment, that receiver sends a confirmation wave backward through time. This is the advanced wave, a kind of echo from the future that travels into the past. The actual particle, the tangible dot we see on the detector, only manifests at the moment these two waves meet and complete a handshake. Its entire existence is the result of this closed loop, a transaction ratified between the past and the future. Imagine shouting into a canyon. The sound of your voice is the alpha wave traveling out. The echo that returns to you is the confirmation wave. In the quantum canyon, the particle is not your voice or the echo alone, but the resonant peak that occurs when they perfectly overlap and reinforce each other. This elegant idea restores a beautiful symmetry to physics, treating the past and future as equal partners in the unfolding of reality. It provides a unique, if mind-bending, solution to the measurement problem. The collapse of the wave function is not a mysterious event triggered by consciousness, but the completion of a transaction. The reason we only see one outcome from many possibilities is that only one specific handshake between a particular emitter and a particular receiver is ultimately completed. All other potential transactions are cancelled out. This interpretation makes a profound statement about time, suggesting that the universe at its most fundamental level is not a one-way street. The future is not an empty page waiting to be written, but an active participant in shaping the present we experience. Every particle that makes up your body, every photon that allows you to see, is the result of a timeless agreement, a cosmic pact sealed across the ages. But what if our observation does more than just select reality? It actually summons it into existence from the void. John Wheeler's participatory anthropic principle takes the fine-tuning argument and turns it into a cosmic drama where we are not just lucky spectators but essential players. He proposed that observers are necessary to bring the universe into being, that the cosmos only achieves a concrete form through the act of perception. This is not about a conscious creator, but about the fundamental role of measurement in quantum mechanics, scaled up to the grandest level imaginable. The universe came into being and continues to exist because we are here to observe it. It is a cosmos that demands an audience. The evidence for this radical idea comes from a breathtakingly strange quantum experiment known as the delayed choice quantum eraser. Imagine sending a single photon toward a barrier with two slits. As you know, the photon behaves like a wave and passes through both slits simultaneously, creating an interference pattern. Now add a twist, place detectors at the slits to see which path the photon takes. The moment you do this, the photon acts like a single particle. The interference pattern vanishes and it chooses one path. Its past behavior changes based on how you choose to measure it in the present, but the delayed choice experiment pushes this strangeness to the absolute limit. Scientists can set up the experiment so that the decision of whether to measure the photon's path or to erase that information is made after the photon has already passed through the slits and is well on its way to the final screen. Astonishingly, the result is the same. If you choose to erase the which path information, the photon acts as if it always went through both slits as a wave, showing an interference pattern. If you choose to measure the path, it acts as if it always went through one slit as a particle. The present observation seems to reach back in time and dictate what happened in the past. It is as if the universe, upon seeing your final decision, retroactively writes the history of the photon to be consistent with what you ultimately discover. Wheeler suggested we could perform this experiment on a cosmic scale using gravitational lensing. Light from a distant quasar can take two paths around an intervening galaxy, much like the two slits. We could, in theory, set up a detector on Earth to decide, after the light has been traveling for billions of years, whether to measure which path it took or to look for wave interference. The implication is staggering. A decision we make today in a laboratory could determine whether a photon that began its journey before Earth even existed traveled as a particle along one path or as a wave along both. Our present observation would be sculpting cosmic history billions of years in the past. This places consciousness, or at least the act of measurement, at the very heart of existence. The universe did not simply unfold in a predetermined way. It waited, a shimmering cloud of potential, until a conscious observer emerged to look back and give it a definite history. We are not just living in the universe, we are continuously bringing it into being with every observation we make, tying the past and the present into a single, participatory knot. The cosmos and the observer are inseparable partners in a dance of creation that has no beginning and no end, only an eternal now of mutual definition. The universe possesses a strange and powerful immune system against paradox. The Novikov self-consistency principle tackles the terrifying logic of time travel head-on, proposing a cosmos that is fundamentally immune to contradiction. It states that any actions taken by a time traveler were always a part of the timeline they are visiting. There is no changing the past because your journey and everything you do there were already woven into the fabric of history from the very beginning. This means the classic grandfather paradox is not just difficult, it is physically impossible. If you travel back with the intent to prevent your own birth, you will inevitably fail. The gun will jam, a sudden noise will distract you, or you will have a last-minute change of heart. The universe will conspire through an infinite number of tiny coincidences to ensure your grandfather lives to have a child who has you, who one day travels back in time. Your free will in this scenario is an illusion, constrained by the unbreakable demand for a consistent timeline. Your desire to change history was always part of what made history unfold exactly as it did. Imagine a novelist writing a time travel story. The characters might feel they are making choices, but the author has already written the entire book. Every action, every decision is fixed on the page to create a coherent narrative. In the Novikov view, our reality is that finished book, and we are simply reading our way through it. This principle transforms time from a linear path that can be broken into a single, immutable loop where cause and effect are perfectly preserved, even when the effect seemingly comes before the cause. You might find an ancient text that inspires you to build a time machine, only to realize once you travel to the past that you are the one who must leave that very text behind to be discovered. The universe does not allow for messy edits, only for a perfect, preordained consistency that locks every event into its destined place. Einstein's cosmic speed limit seems absolute, but a loophole may lie in the fabric of space itself. The Alcubierre warp drive is a theoretical engine that does not push a ship through space faster than light, but instead manipulates the geometry of space-time around it. Imagine a surfer riding an ocean wave carried forward while the water itself remains relatively still. In this concept, a spacecraft sits inside a flat region of space-time, a warp bubble. The trick is to compress the space-time immediately in front of the ship, pulling the destination closer, while simultaneously expanding the space-time behind it, pushing the starting point farther away. The ship itself remains motionless inside this bubble, untouched by the immense distortions it creates as the bubble itself is propelled forward. This is not science fiction, but a valid, albeit exotic, solution to Einstein's own equations of general relativity. It cleverly sidesteps the prohibition on faster-than-light travel within spacetime by moving the spacetime around the vessel instead. The ride would be smooth, with no acceleration forces to crush the passengers, allowing a journey to a distant star in weeks or months instead of millennia. The appeal is undeniable, a dream of crossing galactic distances within a human lifetime. Yet the engineering hurdles are as vast as the cosmos it promises to traverse. To create and sustain this warp bubble, you would need a form of matter that possesses negative energy density, a substance with negative gravity that pushes rather than pulls. This exotic matter is not the stuff of planets or stars, but a hypothetical entity permitted by quantum field theory. While we see glimpses of its effects on microscopic scales, like in the Casimir effect, gathering the astronomical quantities required is far beyond our capabilities. The energy needed is another staggering barrier, potentially equivalent to the mass energy of an entire planet like Jupiter. Even if such power were available, controlling the formation and collapse of the warp bubble presents terrifying risks. What happens to the destination star system when you arrive and release the enormous energy concentrated at the front of the bubble? It could unleash a blast of radiation powerful enough to sterilize entire worlds. The Alcubierre drive remains a beautiful piece of mathematical speculation, a testament to human ingenuity that shows the laws of physics might not forbid the stars, but simply demand a mastery over reality we have not yet achieved. Could our future not be one of building faster rockets, but of learning to fold the very stage upon which the cosmic drama plays out? That desperate scramble to save information unveils a deeper cosmic truth. The holographic principle transforms the event horizon from a simple boundary into the most sophisticated data storage device imaginable. Every bit of information about an object falling into a black hole, the precise spin of every electron, the specific arrangement of every atom, is not lost to the crushing singularity. Instead, it is instantly and perfectly encoded onto the two-dimensional surface of the horizon. It is as if a three-dimensional sculpture were meticulously flattened into a perfect, two-dimensional etching on its outer shell. The event horizon becomes a vast cosmic hard drive, storing the complete blueprint of everything that has ever crossed it. This resolves the paradox with breathtaking elegance. The information is never truly inside the black hole in a way that violates quantum law. It is painted on the surface, preserved for all time. But how does it ever get out? The answer lies in the black hole's slow death. Hawking radiation, that faint whisper of particles leaking from the black hole, is the delivery mechanism. The radiation itself appears random and thermal, a featureless hiss of energy. Yet the secret is not in the individual particles, but in their subtle, intricate correlations. The information is scrambled into the relationships between the trillions upon trillions of Hawking particles emitted over the black hole's immense lifetime. It is like a message hidden not in the words of a book, but in the subtle patterns of the letter frequencies across the entire library. Decoding it would be a task of almost impossible complexity, but the information is, in principle, there. When the black hole finally evaporates in a last puff of radiation, it has returned every single bit of information it ever consumed back to the universe. The cosmic ledger balances. The universe, it seems, does not forget. It keeps perfect records, even if those records are written in the most chaotic, encrypted language imaginable. This revelation transforms a black hole from a destructive monster into a cosmic archivist, a temporary custodian of information that it eventually releases, ensuring that the story of everything that falls in is never truly lost, just rewritten into the fundamental background hum of reality. Our journey through the cosmos concludes with perhaps the most profound and speculative idea of all. The theory of cosmic consciousness proposes that the universe in its entirety is not a dead, mechanical void, but a vast thinking entity. In this view, the entire cosmos possesses a unified, overarching awareness, and our own individual minds are not isolated accidents, but fleeting fragments of this greater cosmic mind. This is not about a God in the heavens, but about consciousness being as fundamental to reality as space and time. It draws deeply from the philosophical tradition of idealism, which suggests that reality is fundamentally mental, and from panpsychism, the idea that consciousness is a universal property of all matter. If even an electron possesses a minute spark of inner experience, then the entire universe, as a colossal collection of such entities, could give rise to a mind on a scale we cannot fathom. We are not just living in this universe, we are the universe experiencing itself. every thought you have, every feeling of love or wonder, is not a private event inside your skull, but a localized tremor in a universal field of sentience. Your consciousness is a wave rising from a boundless ocean of awareness, temporarily believing itself to be separate before it inevitably subsides back into the whole. This represents the ultimate blurring of the line between the observer and the observed. In the quest for a theory of everything, we have searched for a final equation, a set of physical laws. But what if the ultimate law is that the cosmos is awake, that the very act of observation which quantum mechanics places at the center of reality is simply the universe paying attention to itself through our eyes, our telescopes, and our curious minds? The final mystery, then, may not be out in the distant galaxies, but locked within the nature of your own awareness, asking if the thinker and the thought are truly separate, or if both are just ripples in a single, conscious cosmos. 50 mind-bending theories have taken us from a single point of infinite density to the edge of a conscious cosmos. We have wandered through a landscape of cosmic inflation, danced in a multiverse of endless possibilities, and questioned whether the space around us is a hologram or a quantum tapestry. We have confronted dark specters controlling the fate of galaxies and pondered whether our entire existence might be a simulation or a fleeting Boltzmann brain. This incredible journey reveals a universe far stranger and more magnificent than our ancestors could have ever dreamed. Yet the true value of these ideas lies not in their final proof, but in the profound questions they force us to ask. Science is not a collection of answers, but an endless conversation with the unknown, a relentless pursuit that expands our imagination and deepens our wonder with every mystery unveiled. These theories, whether ultimately validated or discarded, are the engines of discovery, pushing the boundaries of what we believe is possible. So we turn this final question over to you. Which of these 50 concepts bent your mind the most? Was it the holographic universe, the chilling great filter, or the solitary electron weaving through all of time? Share your favorite cosmic mystery in the comments below, and if your curiosity is not yet satisfied, subscribe for more journeys to the very edge of understanding.